Comparison test. Suppose that f and g are functions such that 1. The absolute value of f of x is less than or equal to g of x for all x greater than or equal to a, and 2. The integral from a to b f of x dx and the integral from a to b g of x dx exists for every b greater than a. Then, number 1. If the integral from a to infinity of g of x dx is convergent, so is the integral from a to infinity of f of x dx. And number 2. If the integral from a to infinity of f of x dx is divergent, so is the integral from a to infinity of g of x dx. Similar statements hold for integrals of the type the integral from negative infinity to b f of x dx and the integral from negative infinity to infinity of f of x dx. We can see these results graphically. If the integral of the upper curve g of x is convergent means the integral is a finite number, then the integral of a lower curve has to be finite as well, so it is also convergent. If the integral of the lower curve is divergent means it is infinity, or the limit doesn't exist, or the result oscillates between two numbers. Then the integral of the upper curve is also divergent. For example, show that the integral from 0 to infinity of dx over the square root of 1 plus x to the 8th power is convergent by comparison with 1 over x to the 4th. Note that if we were to compare it with the integral from 0 to infinity of 1 over x to the 4th, we won't be able to use the p integrals. But we know that the integral from 1 to infinity of 1 over x to the 4th dx is convergent. So we will break the integral 0 to infinity dx over the square root of 1 over x to the 8th into two integrals. One go from 0 to 1 and the other one go from 1 to infinity, so that we can compare the latter with 1 over x to the 4th. The first integral on the right hand side is over a bounded interval, so it is convergent. It will be a finite number. The second integral can be compared to the integral of 1 over x to the 4th by observe that 1 plus x to the 8 is more than x to the 8. The square root of 1 plus x to the 8 is greater than the square root of x to the 8. The square root of 1 plus x to the 8 is therefore greater than x to the 4th power. Their reciprocal is the opposite. 1 over the square root of 1 plus x to the 8 is less than 1 over x to the 4th. This shows that 1 over x to the 4th is greater than 1 over the square root of 1 plus x to the 8. The graph of 1 over x to the 4th is above the graph of 1 over the square root of 1 plus x to the 8. But we know that the integral from 1 to infinity of 1 over x to the 4th dx is convergent, and it is the graph above. Then the integral of the function of the graph below must be convergent as well by the comparison test. So the second integral is convergent. The sum of two convergent integrals is convergent, so the given integral is also convergent. Show that the integral from 1 to infinity of dx over the square root of 1 plus x squared is divergent. The integrand 1 over the square root of 1 plus x squared, if we were to look at the leading terms only, because the leading terms will determine the end behavior of the graph, then we would notice that this integrand looks like 1 over the square root of x squared, or 1 over x. And we know that the integral from 1 to infinity of 1 over x dx is divergent, because this is the p integral when p equals 1. We know the integral from 1 to infinity of 1 over x is divergent. To compare some other integral with this divergent integral, we would need the other function to be above this function y equals 1 over x. We start with the obvious statement, 1 plus x squared is greater than x squared. Thus, the square root of 1 plus x squared is greater than x squared. So 1 over the square root of 1 plus x squared is less than 1 over x. Since the square root of x squared is x, now these x are positive because the integral is over the interval 1 to infinity, x are positive. This shows that 1 over the square root of 1 plus x squared is less than 1 over x. It is below 1 over x, so we cannot use the comparison test. The comparison test is useless if the integrand of the integral that we want to compare it to is below a divergent integral. To use the comparison test correctly, we need to have a good working inequality. If we do not have a good inequality with the good condition, then the test is not useful. If we know that a certain integral is divergent, then we can only say that the integral of the integrand that is above it is also divergent, not when it is below it. Thus, we need to show that this integrand is somehow below a divergent integral. Observe that for x is greater than or equal to 1, this is a very clever trick. 1 plus x squared is less than or equals x squared plus x squared because x is greater than or equal to 1. Thus, the square root of 1 plus x squared is less than or equal to the square root of 2x squared, or the square root of 1 plus x squared is less than or equal to the square root of 2 times x. So 1 over the square root of 1 plus x squared is greater than or equal to 1 over the square root of 2 times x. And we know that the integral from 1 to infinity of 1 over x dx is divergent, so 1 over root 2 times a divergent integral is still divergent. The advantage of this is that we now know that 1 over the square root of 1 plus x squared is above the divergent integral, so by the comparison test, this integral is also divergent.